These bottles of Coke every day.
I'm not very loud.
Okay. All right.
I've spent 1,693 powders.
We're ready. Oof, that was a long day, huh? Okay. So I don't have a set of questions for ashing. It's pretty easy and straightforward. I just want to continue where we left off. And you did ashing in lab, so um, so nothing too crazy. Dry ashing has a lot of advantages using the muffle furnace. So basically, we put the crucibles when the muffle furnace is cold, and then you close it and you let it heat up on its own. That's why we consider it safe. Unless we do something crazy like heat it up and try to put the crucible, which is this is not safe. And we usually part of safety training, we tell everybody do not do that. You just put your crucibles in when it is cold. And then when you want to take it out, also you wait until it's completely cool before you open it and try to take out your crucible. Um, so usually it's safe. A couple of years ago, one incident happened, and actually it was an undergraduate researcher in my lab, very new, although went through the safety training, but did one little mistake, and it was the glove that you would wear to protect from any potential heat was on top of the muffle furnace instead on the side. And then when the muffle furnace was open before it was completely cold, it was set on fire. Yeah. Yeah. But nothing happened to the researcher. But after that, we made sure to tell everybody, hey, listen, you don't come close to it until it's really cold, and don't put any potential hazard that can burn on top of the muffle furnace. You remember that incident? Were you there? Yeah, it wasn't Andressa. Okay, so it's generally safe. Little attention is needed. You just turn it on, leave, come the next day, turn it off. So not much to do. No reagents or blanks. You just weigh your sample, and then depending on the size of the muffle furnace, you can put very many crucibles. I think the one downstairs can take maybe 20 crucibles at a time. Disadvantages is lengthy. We have to at least leave it overnight, 18 to 24 hours at this high temperature, so it takes time. The equipment originally is expensive, and it needs to be under an exhaust system so that all of the fumes get sucked up and they don't come into the room. But once it's there, it's there. It's a workhorse. The other disadvantage of using dry ashing is actually volatile minerals get volatilized, like iron, zinc, copper, phosphorus. So that's why when we're really after analyzing these elements, we try to reduce the temperature and assist the oxidation of organic matter using a little bit of nitric acid. So usually we heat at 400 to 450 degrees, take it out, put a little bit of acid, heat it on a hot plate, and then put it back in the muffle furnace at lower temperature. But if we have the capability to do wet ashing for these elements, volatilizing, like volatile elements, we do wet ashing. And I'll talk about wet ashing in a little bit. What can you imagine sources of errors could be from what you did today in the lab? What could be sources of error? Very easy.
Sample prep?
What's that?
Sample prep?
Sample prep, absolutely. Sample prep, first of all, you need to make sure your sample is homogeneous and the sample you take out is representative of the entire sample. How do you grind it? Do you grind it in something that can get the sample contaminated with other elements or minerals? So that is one thing we need to avoid. Also, what we did for cheese is pre-dry. So we need to make sure that during pre-drying, we don't lose samples, so that we don't mess up the estimation of ash content. And also, did you guys burn off the fat, the cheese group? You burned off the fat to avoid potential fumes and loss of sample while dry ashing. So we need to avoid that. Another example of potential error is, like I said, the volatilization of elements. So if you volatilize iron, copper, zinc, and phosphorus, you might get an underestimation of your ash content. Not only an underestimation of the minerals if you're using the ash for atomic absorption or determination of mineral, you also get less weight. So you underestimate. So volatilization of elements lead to underestimation. If I ever ask you in a test, what could be possible underestimation errors? Volatilization of elements. Incomplete combustion, meaning you still have organic matter in the ash. So the ash usually would look like black or gray, dark gray. So this means there are some organic matter still left. Does that cause overestimation or underestimation? You think? When there's organic matter still left in your crucible, and then you go to weigh that crucible, and you subtract the weight of the empty crucible, overs. Yeah, so incomplete combustion causes overestimation. All right, now take out a piece of paper for +2. I know you're eating. Try to multitask. And let's solve this. So it's very important to determine things on wet basis and dry base. And sometimes we need to convert dry to wet, like the case of cheese. We pre-dried, so we get the ash content on dry bases, we get the fat content using substrate on dry bases. What if we want to know as is basis? So we really need to be able to convert wet to dry and dry to wet. So take a moment, couple of minutes, and try to determine the ash content on dry basis. So this is given to you as 1.14% ash on wet basis, and you are given the moisture content of 47%. So now convert to dry basis. Dry basis meaning you want to take the ratio of the ash to dry matter. Okay, so the ratio of ash to dry matter in a percentage format. Okay, so with that, try to calculate. You have an answer. You can tell me. Yes. 2 point? Correct. So it's 2.15 So what we did again is taking the ratio to the dry matter. So now we're talking all in percent. So 1.14 is a percentage. So you multiply by 100 and divide by the percentage of dry matter. The way to get the percentage of dry matter is 100 minus 47, which is the moisture content. So basically, what this tells you so if you have 100, if the percentage says if you have 100 grams of as is sample, you have 1.4 grams of ash. 1.4? 1.14. Okay. Now on dry matter basis, so in 100 grams, how much dry matter do I have? I have 47 grams of water, so my dry matter is 100 minus 47, which is 53 grams. So if I want to get the ratio of the ash to the dry matter, it would be 1.14 over 53 times 100, and that gives you on dry basis, 215. In order for you to know that you did the correct, you put the correct denominator and numerator, the dry matter on dry basis is always higher than on as is basis. So 2.15 is higher than 1.4 because you are dividing by only the dry matter content. So that's portion of the whole. When you are dividing by a portion of the whole, then your value will be higher. So dry base is always higher than wet bases. So this is how you would know that you did the right equation. Any question about that? Happy to repeat. All right, very good. Now this is a little more complex. On that same piece of paper, now what I'm telling you here, determine percent ash on fat-free basis. Now you would tell me, why is this important? It is important because if you have a hamburger that is very moist and has very high fat content, before you do the ash, usually you dry and defat, then do the ash, then ash it, so that to avoid any splattering in the muffle furnace. So this exists. Percent ash on fat-free basis exists. So, but here is just an exercise for us to practice calculations. All right, so here I want the ash content on fat-free basis, not on a dry basis. So we have the ash content on as is, on what basis. Now I want to determine it on fat-free basis. Before I give you any further hints, I need you to think about how would you go about it. So you're given here the percent moisture, you're given the percent fat on dry basis, mind you, because they might have done Soxhlet, so they dried the burger before getting the fat content. So there's two-stage things you need to do and pay attention to. The fat is on a dry basis. But what we're asking you to get is the ash on a fat-free basis, not on a dry basis. All right, think about it for a minute and see if you can solve this puzzle. Okay, anyone would know what the first step would be? What are you doing as a first step? Are you raising your hand, William?
Convert the fat percent to wet basis.
Yes, that's exactly it. The first step. Convert the fat percentage to wet basis. All right, take a moment, think how you do that, and let me know when you have an answer. $29 point? Absolutely. So round it up to 30%. Did everybody get 30%? What, Ali? What? That's okay. That's totally fine. Did anybody else raise your hand if you got 30%? What? Luke one got 30%. William got 30%. Caitlin, what did you get? Question mark. Raise your hand if you got question mark. All right, I love it. Okay, you got question mark. That's why you're here. All right, so what 56.6%, it's telling me now that I have 56, what was it, 6? I forget. I'm Dory. 56.6 short-term memory loss. Okay, grams of fat in 100 grams of dry matter. But really, how much dry matter I have in my wet sample?
What's, well,
47 is moisture, so how much dry matter I have in 100 gram of wet sample? 53. Yes, 100 minus 47 is 53. So in my hamburger sample, I have 53 dry matter. So I have 56.6 grams fat in 100 grams of dry matter, but I have 53 grams of dry matter in my original wet sample. So how much do I have fat in 53? Okay. So this means I have 56.6 grams in 100 grams of dry matter. How much do I have in 53 grams? What is the number? 30%, right? Okay. I do this like with all my heart. Use 10 markers. Okay, 30. All right, now that we know that the fat on as is basis is 30%, how would I calculate percent ash on a fat-free basis? I know now it's 30% fat and as is wet basis. Okay, give it a, yes.
Could it just be the same way that you calculated it before, but instead of using the water, you use the fat that you just calculated?
Yeah. Absolutely, you got it. So do that. Tell me the number instead of question mark. Tell me the number now.
Why did we do that?
What
Like,
would?
why did we do what Ali just said?
Because now I'm fat free. instead on water-free, which is usually the dry bases,
Yeah.
now it's on fat-free.
So, but then we just redo it, with the water in it.
Yeah, so the water is in it. So you just divide by 100 minus fat rather than the 30%.
So would you ever do fat free and water free?
You could. And that would be
We
different
would just minus
calculation.
both of them? Yeah. From 100?
Yeah,
Okay, okay, so that makes
Yeah.
sense. Mm-hmm.
all right, so what did you get, Ellie?
1.63.
Absolutely.
So what? The numerator.
What on the top? Numerator, right? Numerator, whatever that is, that the top. Yeah, so 1.14, and remember it's a percentage. That's why we say in 100 grams. So you, and then here, instead of subtracting the water, you subtract the fat. So it's 100 minus 30%.
So it's saying the amount of, oh, I see, the amount of ash in the sample.
Yeah,
Without
without fat in
yeah.
this case, yeah. Absolutely. And Lizzie asked, can you do without fat and without water? Yes, we can. So then it would be, the denominator would be 100 minus 30 minus 47
So then it's solids without water and
without fat, if you want to get on just fat-free, water-free basis. Yeah, so what would be that number? I should add it. What would it be? So it would be 1.14 times 100 over what? Over 23. Right? Over 23. Yes. That's correct. What did you get? You add that to your, I want to add it also.
I'm just curious.
What do you mean? We are learning. It's fine. On fat-free and on dry bases, it would be equal 1.14 times 1.14 times 100 over 100 minus 47 minus 30. Then we get equals what? 4.96. And actually, this would be the value you would get in the hamburger, because you are going to dry it, defat it, then put it in the crucible and ash it. So this is the ash value that you actually will get. And then you work yourself backward to get the 1.14 in the actual sample. Very good. All right. So the last bit of the ashing is wet ashing. So in wet ashing, you're doing the same thing. You're getting rid of organic matter, but it is wet because you're digesting with acid. You're not putting it in a muffle furnace. You are digesting your sample with highly corrosive acids. And also you're going to use heat. It's not like without any heat. You will heat it to 200 degrees C instead of 500 degrees C. And under the hood, and with an exhaust system that takes all the fumes. So what happens is, when you are heating in the presence of concentrated acid, so do you have a question? Okay, dark color and fumes will come out. So your organic matter is being combusted and oxidized and burns up. So your CO2, SO2, NO2, H2O, all of that will evaporate. So it starts with like very dark color and fumy, and then when it's fully digested, it would be either clear or straw yellow solution. then all of your minerals are solubilized in the acid. So in this case, you don't need that. Remember when you did the atomic absorption, you had the ash and you had to put concentrated acid and solubilize. This is already in solution for you. Now, the acids used are typically nitric perchloric, but perchloric is very, very corrosive. It requires its own hood, perchloric certified hood. Therefore, not everybody has perchloric certified hoods. Therefore, most of the folks that use wet ashing do sulfuric with nitric, both concentrate combination. And then yeah, they do the digestion. So we do have nowadays we do have digestion units to do that, where it's a block that you would put your tubes in and it will heat at 200, but you have to do it under the hood for the fumes or with an exhaust system. We always run a reagent blank to account for any contamination that comes from the acids used, nitric, perchloric, sulfuric. So any contamination of minerals that come from these acids. So that's why a reagent blank is used. Now, advantages, minerals remain in solution. If we're doing mineral analysis, and this is what it's used for mineral analysis, we don't have to solubilize it. They are in solution. And because the temperature is low, we don't lose volatiles. So iron, copper, zinc, phosphate, or phosphorus, we don't lose them. During the dry ashing, we might lose some of those because they're volatiles. So that's the advantage. So if we're doing pure iron analysis, and we can do wet ashing, it's recommended to do wet ashing over dry ashing. And oxidation time is short. You don't have to leave it 18, 24 hours in the dry, in the muffle furnace. However, since we're working with acids, you have to have the safety training, you have to have the correct hoods to use, and you need constant operation attention. So it's not safe, but you can be trained to work with it safely. And then sometimes you're limited by the number of samples. Depending on the digestion block you have, you might have 6 spaces or 12 maximum that you can digest at one time. Now, you can do microwave ashing. It's not official method of analysis for most food. They have been validating it with few types of foods in comparison to regular ashing. And with microwave, you can do wet ashing and you can do dry ashing. So analysis time is very, very short. It could be in minutes, from 5 minutes to 30 minutes. And then you can operate under pressure so that the boiling point of the acid is increased, so you have better efficiency of digestion. Therefore, you can use less corrosive acid. You can just use nitric acid on its own. You don't need combination because now you increase the boiling point under pressure. And you can do multiple samples. Actually, this picture, oh, this picture here on the left to you. So we do have this microwave in one of the small labs in the department, and we use it for something else, digestion, for proteins to determine amino acids. But it can be used to do microwave digestion to get the ash mineral content. But do remember, with wet ashing, you don't actually get a weight of ash. So it's not used to get percent ash. It's used for mineral analysis specific. Because all your minerals will be in solution, you do your series dilution, and then you can determine your element content. But it's not used to calculate total ash. So wet ashing, remember, is not used to calculate percent ash. All right, so 2 systems, you can get that system that is closed, that can work under pressure, and you can get the large system that is not pressurized and you can, but you have less number of samples that you can analyze. And then finally, microwave dry ashing. So you can also like the muffle furnace, but instead of the furnace, it's a microwave and it's much faster. But again, it's not validated for all foods as an official. All right, let's work on this. You don't have to put it on your sheet. You can have we just have discussion. So think about it for a minute and we'll answer the first question. Yeah.
And what happened if it's using acids and oxidizes,
So you agree with your boss?
that it's faster. It always helps.
Do you agree or disagree with your boss concerning the time issue? Yes. Okay. With the time issue. Okay. What about the second one? Not considering the time issues, why might you want to continue using dry ashing? Yes.
There you go. No. My God, I'm gonna throw it away, ashing doesn't give you your ash percent.
Yes, what ashing does not give the total ash content because your ash is dissolved in the acid. So it's for mineral analysis. If you want to get percent ash, which is important, for example, in flour milling. So when we're doing wheat flour, sometimes you have whole wheat flour, sometimes you have partially refined flour, and sometimes you have refined flour. And then there are standards for ash content for refined, partially refined, and whole. So if you want to just check your milling process, if you work in a flour mill, like I did for a year after my master's degree, you would spend a lot of time doing ashing and confirming the ash content to determine, yeah, this is refined, good to go. Oh no, some filters are broken. We have more bran than needed. So you need the total ash content. So why might you change to wet ashing? Just yeah, if you're doing mineral analysis and specifically you want to get that iron for the label, you don't want the percent ash, or you can do percent ash using dry ashing, but still do wet ashing to do the iron determination for more accurate and to avoid volatilization issues.
Specify.
Huh?
Why do you specify?
Why do I specify iron? Because it's volatile and it's one mineral you need for the label. Yeah, so if you want to really get your iron content, especially if you want to make a claim or if you want to make sure that you are reporting the correct amount within that 80%, 80 to 100%. Thank you. Especially if you fortify with iron and you're making a claim, you definitely don't want to underestimate. Yeah.
Is dry ashing cheaper than wet ash?
Yeah, well, cheaper and easier, but originally you have to put a lot of money to get the unit. It's expensive, but once you have it, it's cheaper. With the wet ashing, you need to maintain the hood, you need your reagents, you need training for safety. So all in all, takes more cost per sample. Okay, so sometimes I tell you in an exam, make up your own data. I just tell you, make up your own data and determine percent ash in whatever sample. If you want to make up your data and then you give me percent ash of 20%, this is a lot. Big. So it's just, usually ash content is pretty low. Yeah, so just keep that in mind that usually ash content is not very high. And that's it. I have 7 minutes to start the best topic of it of all.
Don't say it. Don't say it. No. You gotta get too happy.
What?
Too happy. I'm just as happy.
What's
I
that?
have a question.
Yes?
What's your rosebud and thorn of the week?
What is what?
Your rosebud and thorn. Your rose is something that you're happy about because it's like beautiful.
Oh my
Your
God.
thorn is something that's like stabbing you inside. And then your bud is something that you're looking forward to because it's gonna grow into a beautiful rose.
For this particular
This
week?
week, yeah. I'll ask next week as well.
So the rose one, I don't have very many exciting things. Is
Oh.
seeing you all this week.
Don't lie.
Seriously, my life is boring, so. And then the thorn, I haven't seen my daughter for almost 2 weeks. Well, I was traveling and she's married now, so I don't get to see her very often. But we're looking forward to, we're going to Apple Orchard this Sunday.
Team photos.
Yeah.
Which orchard? Show and tell.
I have no idea, they're taking me. I don't know, but yeah, thank you. You were distracting me so I can let you go, but I'm gonna start the I'm gonna start protein analysis, the best topic on earth. Who agrees? -2 to Africa and Resa Racer. Okay. So the reason I ask this question is oftentimes for research methods, we determine protein content by doing UV absorption, especially at 280. So what absorbs among the amino acids? Which amino acids absorb light at 280? Aromatic, aliphatic, tryptophan? Huh? What did you say? Okay, Emma is not wanting me to hear her.
I don't know what I'm doing.
So what did you say, Lily? A, just A, B,
I don't know what that means.
it's A and C. Well, tryptophan is aromatic, so A and C. So the aromatic component of the amino acid is what absorb light. Aliphatic amino acids are useless. No, they're not very useless, but they don't absorb light at all. So the aromatic, this is just a refresher from your food chemistry, aromatic tyrosine, tryptophan, phenylalanine. So almost all, not almost, all proteins, food proteins, have some of these, a proportion of these amino acids. There is not one protein that doesn't have any aromatic. Therefore, proteins will absorb light at 280 because all of them have a certain proportion of these aromatic amino acids. And if we want to dig a little deeper, every amino acid have different absorptivity. So that means some of them absorb more light than another at 280. So phenylalanine has the highest molar extinction. We talked about that in spectroscopy section, the molar extinction, and tyrosine comes next. Tryptophan is the least one, but it does absorb light. Okay, so reminder about peptide bond, and I'll tell you why it's important in a minute. Which is true for peptide. Is it a covalent bond? It says a covalent. It is a covalent. It's a covalent. It's not an ionic bond or hydrogen bond or hydrophobic bond or van der Waals. So it is a covalent. Okay. Anything else is true here?
See.
So it is a bond between amino groups of 2 amino acids. Do you agree? You all agree?
Yeah.
Who's in food chemistry right now?
Wait, don't read. She's gonna tag on this morning.
In proteins? In protein?
Isn't it between the amino group and the carboxyl group?
Yes, thank you.
Okay.
Thank you. Good job. It's the carboxyl, the carbon of the carboxyl group and the amine, the nitrogen of the amine group. So it's A and A and B. It's a covalent bond. So it's a condensation reaction. So amino acid and amino acid, they bond covalently, water molecule comes out.
But isn't it between the amino group and the carboxyl group? Yeah. So it wouldn't be B or C. Oh, yeah.
Oh, I misread. Yeah, so it's just A. Scratch. So it's just
Oh my goodness.
just A. Oh my God. Thank you, Lizzie. You keep it. You want to teach?
No.
Yeah, for some reason my eyes saw that B is a carboxyl and amine, but no. Yeah, I got tricked. So no, it's between the carboxyl and amine group. So only A. All right, before I let you go, I have 1 minute. Tell me why it's important.
Nutrition label. You told me it's a double major.
All right, I wish you were that fast in College Bowl. All right, yeah, nutrition label. What else? Who cares about carbohydrate, Lizzie? Come on, we're talking protein. Yeah. Yes, okay. All right, yeah.
Protein, like, digestibility, yeah.
Oh, yeah, so we need the protein content for biological determination. Yes, very good. What else? Yes, if you want to make a claim, you need to have a certain amount of protein to say high protein content or a good source of protein. Yeah. So, but also quality control. So you need a certain amount of protein in a final product. So you would just monitor protein content during processing, milling, drying, what have you. So quality control, sometimes standard of identity. Yes. Stability. Oh, yeah. Of what?
Like, yeah.
Of what?
Yeah.
A foam? You're close. So if we want to measure functional properties, we usually determine it per 1 gram of protein. So like emulsification, how many milliliters of oil is emulsified by 1 gram of protein? What's the volume of foam you can get in a solution that has 1% protein? So usually functional properties, or if we do gelation, which protein gels at 5% protein solution or 15% or 20%? What's the percentage of protein that gelatin would gel at? Huh? Gelatin that is used in jellies and stuff like that. Huh? 1%. So if you look at the label of a jello or a jelly that is in the market, you'll see that there's 1 gram in 100 milliliter or something. Yeah, of gelatin. So that brings that.
1 to
100. Yeah. What about pea protein?
You told me.
Andressa. It's really bad. 20 grams.
Oh, yeah.
In 100 milliliter for it to gel. It's pretty bad. Anyway, but so functional properties, biological activities, or enzymes, for example, if we want to determine the activity of an enzyme, so standard units, we usually determine it per gram of protein because enzyme is a protein. Okay, there's so many methods. I'm going to let you go in a minute. So we'll talk quite a bit about Keldar and Dumas. We'll run them in the lab. These are standard methods of analysis. Infrared needs calibration, secondary method for quality control. And then we have a bunch of research methods. And you go have fun. I'll see you on Friday.
Give me your papers. Are we turning these in?
Yeah, to Andressa. Turn in your paper.